Hi, welcome to our N2Vision demonstration. Our system is designed for a variety of agricultural users, allowing the management of multiple farms easily from the same map. We have provided a geocoded search to quickly take users to desired locations. This enables users to quickly and easily set up new farms and move between them by clicking the map icon or selecting it from the list of user farms, and facilitates diverse users with a need to manage multiple locations. Users can add their fields to the application, naming them as desired, and providing necessary information such as the type of soil before outlining the boundary directly on the map. The system calculates useful data such as the area of the field and provide the user with numerous tools to interact with the map, enabling them to highlight, label, and measure areas of the field and exclude them from analysis and interventions. Our innovative N2Vision AI analysis can provide precise measurements of nitrogen within the crop and soil from user-supplied imagery. Users can upload images from many sources such as camera phones, robots, and drones. This shows how users can upload orthomosaic drone images to the system. The preview helps the user confirm the correct location within the field and select the date of the survey, if not available from the image metadata. Once uploaded, the images are processed and reprojected for use in the system before being analyzed with our unique AI models. Users can easily pan and zoom the orthomosaic on the map to get a detailed view of the crop or analysis, as well as numerical values for each location. Numerical values are provided for each location superimposed on the analysis map using calibrated color mapping and suitable legends. This is combined with metrics calculated during the analysis with aggregated results available at a glance. Groups of individual images can be uploaded also whether from a field walk or drone sampling flight. Each image is analyzed and placed in the correct geolocation, allowing us to interpolate values across the field. Each image is considered as a data point within the field, undergoing the full range of our advanced analyses, which can be easily accessed by the user in the same interface with additional controls to select and step through all the images. These data points can be further processed using statistical and geospatial algorithms to interpolate the analysis results across the whole field to provide approximated coverage for downstream applications. As part of our project, we have conducted experiments over 2 separate years and across 2 different fields to collect the data used to train our innovative AI analysis. This included detailed orthomosaic imagery throughout the growing season and covered a series of experimental plots with varying amounts and types of fertilizer applied. The timeline allows the user to easily view crop changes over time, both in the images and analysis results. Our model detects numerical values for nitrogen in the leaves and soil. Combined with biomass data acquired from measuring the plant structure, we can determine the soil nitrogen supply. As biomass data was unavailable, we have estimated it for this demonstration. Current best practices rely on index calculations of the images which we have included for comparison. Our application clearly demonstrates that our advanced AI provides better, more insightful data than these simple RGB indices, as can be seen. The second experiment covered double the area of the first year, investigating both amount and type of fertilizer application to winter wheat. Our AI was able to learn features that enables it to distinguish between these applications and amounts utilizing them to determine a numerical amount for nitrogen status in the plant and soil. The crop timeline can be filtered and sorted by the type of survey or management intervention, as well as the date, to ensure the wanted information is readily available. Our system is designed to reduce nitrogen usage, saving resources while optimizing yields. By leveraging our advanced AI analysis, the system can determine the nitrogen status in the plant and soil at an extremely high resolution. It can then use this data to determine the requirements of the plant, generating a detailed prescription map showing the precise amount to be applied. This maintains yields while reducing excess application, saving resources and costs. Users can generate a prescription map based on our analysis by first setting the number of applications over the season and the size of the application unit based on their machinery. This can be downloaded as a shapefile for universal use. The system will find the latest analysis and calculate the recommended nitrogen, adjusting the amount based on previous and remaining applications. Once applied, the application results can be uploaded as verification to ensure correct values are used subsequently. Here, the applied nitrogen was part of our experiment with red representing high amounts of nitrogen, yellow medium, and green low. Black represents zero nitrogen application. Our demonstration clearly shows that less nitrogen is needed in the areas of high application. Over time, we can see, by the black areas, that no more nitrogen is needed in the plots receiving the maximum amount of fertilizer during the experiment, whereas the plots receiving low or zero amounts require high amounts to be applied, represented by the red areas. N2Vision is designed to complement autonomous agricultural robotics for both nitrogen status monitoring and precision application. To demonstrate this, we have created an autonomous scouting integration using a Spot robot from Boston Dynamics as a proof of concept. Users can add their farm robots into the system, allowing for automatic management and analysis. Robots are given a home location where they are docked and can automatically return to if there are any issues. In this case, we have created our own service to manage the connection and control of the robot directly. But we envision integrations with manufacturer control platforms as well. The Spot robot is a quadruped with 6 cameras used for autonomous navigation and an additional camera in the gripper of the mounted mechanical arm. Once connected, the status and location of the robot are monitored when in range of network communications, while telemetry and camera feeds can be accessed directly in the web application from anywhere by the farmer. This allows the system to notify the farmer of any problems and provide emergency controls for remote interventions. After a robot has been connected to the system, users can plan high-level missions utilizing the robot to perform suitable tasks such as scouting or spraying the crops. Users can select the type of mission required and then choose a suitable robot from the filtered list before selecting a series of waypoints where the mission actions should be carried out. Our platform can assist by automatically generating a suitable selection of waypoints within the field on a continuous path to minimize travel. But users can also manually select specific points and adjust them as necessary to achieve diverse mission outcomes. For our demonstration, we have created 3 waypoints in our robotics lab mapped to 3 geographic locations near our test field. Once complete, the mission is uploaded to the robot, which acts independently, autonomously navigating to each waypoint using its own systems, ensuring mission completion without network connectivity and allowing the robot to manage emergent issues. At each waypoint, the robot performs the required action. Here, Spot is taking a photograph of the crop. While connected, location and mission status are available in the web application, along with low-resolution imagery from the waypoint data capture. Successful waypoints are indicated by green backgrounds, while errors are displayed as red. Once complete, the robot returns home to dock and then uploads high-resolution images directly to our system for processing and analysis. Users can access these in the same manner as drone and manual surveys, with the captured images displayed alongside their location and the analysis results. All our innovative AI analyses can be autonomously collected and processed, opening the door to fully automated robotic diagnoses and interventions. Finally, we have incorporated an AI chatbot to provide users with agricultural information. Our AI uses a retrieval augmented generation method to ensure that only accurate responses are provided. For this demonstration, the chatbot is limited to materials provided by AHDB regarding wheat and RB209. While users can ask any question, the AI has been instructed to limit responses based on the available information, informing the user when it cannot answer the question. Thank you.